All right, we have another example. We have a child riding a Ferris wheel. So the big wheels that have place to sit or stand and rotate. I don't remember which way they rotate, but rotate vertically. So you're going up and down and up and down. So we have the mass of this child, the radius of this particular Ferris wheel, 10 meters. It's traveling in a vertical circle. They're telling us that it completes one revolution in 10 seconds. A revolution means a full circle. So one revolution would be 2 pi radians. So we're saying pi over 5 radians per second. This is our angular speed. You can think of it as well as a rotation rate. It's telling us the number of radians per second made by this Ferris wheel. This particular problem is asking us for the magnitude of the force on the child by the seat at the lowest point. So down here, when the child's at the bottom, we want to know how hard this seat is pushing up on the child. So again, free body diagram. We know there's a normal force upwards from the child sitting on the seat. We know there is a force of gravity downwards. We know they cannot be equal in this case because the child is going through circular motion. Their direction is going to change. So because they're following a circular path, they do have a centripetal acceleration. That centripetal acceleration always points towards the center. So when they're at the bottom, that centripetal acceleration points upwards. So the net force must point upwards. That's going to mean the normal force is bigger than the force of gravity. So when we write out the net force along this radius line, it needs to equal the mass times the centripetal acceleration. So upwards towards the center is the normal force. Downwards away from the center is mg. Those are the only forces along that line. So this needs to equal mass times acceleration, and specifically the centripetal acceleration. Now we have 2 ways of writing centripetal acceleration. V squared over r, where v is the speed in meters per second, and r is the radius of the circle. The other way is r times omega squared, where omega is the angular speed. In this particular case, the information they gave us allowed us to quickly find omega. So that's what I'm going to plug in for A is r omega squared. We know the mass of the child. We know the radius. They're asking us for this normal force. And so we can plug that in. I'm going to factor the mass out just for simplicity of plugging things in. So r omega needs to be squared. So 687, at best we have 2 sig figs. The force on this child from the seat when they go down through the bottom will be 690 newtons. that's bigger than the force of gravity. mg acting on them, 50 times 9.8 would be 490 newtons. So they feel heavier at the bottom. When you think about riding a roller coaster, the normal force represents what we feel. If we feel heavier, it's because the normal force is bigger than our normal weight. If we feel lighter, if we feel like we're lifting off the seat, the normal force would be less than our actual weight.